Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course. And as always, it is an honor and a privilege to be serving you, as it is every day here in my virtual classroom. So come on inside, I got something I want to teach you. Not about the XFL, however, I do recommend that you get a good watch of this. 4 games every weekend, 2 on Saturdays, 2 on Sundays, 8 teams, 10 weeks. Awesome rules that encourage a lot of offense and a lot of lack of dead air time. But no, not going to teach you about that, although Seattle and Dallas are playing on my screen here right now. What I am going to be talking about instead is linear inequalities. Mr. Robinson, you've taught us about linear inequalities. Oh, yeah, sorry. Systems of linear inequalities. Oh, Mr. Robinson, you've taught us about systems of linear inequalities too. Oh, that's right. Oh, creating systems of linear inequalities from word problems. That's right, kids. That's what we're going to be doing today. Taking word problems, creating systems of linear inequalities, and then giving that its go. This is actually, even though a lot of people are like, I don't like word problems, the inequalities is too much, believe it or not, this is one of the relatively more fun lessons here because of its really concerted tangibleness that there is to this. And what I mean by that is you really understand what it is you're looking at, what your solutions mean, you know, how you can interpret the stuff. And it's kind of nice how the math really restricts you to see what your options are. You'll see what I mean when I do it. I do have 4 practice problems for us to go over. And by the way, right after this video, I'm going to be going straight into a whole mixed review, cumulative review of creating the word problems from systems of equations. Creating the systems of equations from word problems. Creating or graphing systems of linear inequalities, and then creating word problems from systems of linear inequalities. So a nice review for that as my students are looking to test at the end of this week. So if you see this video before I upload the next one, know that that one's coming today as well. All right, so without further ado, let's go ahead and get started. I have 4 problems, like I said, to show you. Here's my number 1 in bold. Here's the situation. We're going to go ahead and answer some stuff. All right, number 1. You need at least 3 pounds of fruit to make muffins. Blueberries cost $4 per pound, strawberries cost $3 per pound, and you can spend at most $21 on fruit. Write and graph a system of linear inequalities, and after that we'll be doing some more stuff. Okay, so before I actually officially begin, one thing I do want to make sure that you know is that as we write a system of linear inequalities, even though it doesn't say it, we still need to make sure to define variables. We need to make sure we let them know what x and y are. And I'll be specific about using x and y this time. Even though it looks like, hey, I could use B for blueberries, S for strawberries. The problem is we're going to graph it. And I want to make sure that we do understand what the x coordinate pair and the y coordinate pair is. And if we define it as such, we'll be able to look at that each time. That's number 1. Number 2 is you might be asking the question, well, this word problem type looks very similar to what we were doing from systems of equations. How do I know this is a system of linear inequalities, and how would I know that generally without them asking me, telling me? And furthermore, how do I know the less than or greater thans for it? So to answer the question first, how do I know it's not a system of equations, besides the fact that we said system of inequalities, is there are some words like this one, at least, and at most. And there, you might see no more than or no less than, something like that. These kinds of words say that you don't have to land right on those values. I don't need exactly 3 pounds of fruit. I can have more. And I don't need to spend all my $21. I can spend less. I can choose to spend none if I really wanted to. However, I still need to buy the 3 pounds of fruit. So there's this nice happy medium that the graph is going to show us based on the equations that we write that say there's some flexibility in your options. And I don't know if you recall, I was talking to you guys the other day in my previous video about the fact that you can have an infinite number of solutions for these shaded problems, either an infinite number or no solution. I'd say there's never just one solution. In these particular instances, that might not necessarily be true because we are now crossing through these shaded regions where we're only sometimes looking at integer solutions. And you're actually going to see here, I'm going to restrict how many solutions we can actually have. But you'll be able to make sense of the solutions as we do them. All right, so let's go ahead and get into these problems here. Let's start by defining variables as I just mentioned before. Let's start it off with, let's let x equal the number of blueberries because we know the cost. We need to know how many blueberries we're going to purchase. Ooh, someone just took it to the house. Oh, never mind. That was a kickoff or punt. I don't know what that was. I just thought someone just took it to the house. All right, number of blueberries that you're going to purchase. I'll just put number of blueberries. And then I'm going to let y equal number of strawberries. All right. All right, now we're going to create two inequalities to create a system for this. And I'll let you know there are some problems where we create more than two. Actually, here, I'm going to talk to you also about what are called implied inequalities. And you'll see what I mean when I do them. All right, so let's go ahead and construct this system here. I'm going to do one based on the amount of pounds. Oh, you know what? This isn't number of blueberries. It's number of pounds of blueberries and number of pounds of strawberries. Good thing I need to be a little more specific on that. That is my mistake. I should have read the problem again. It's not blueberries cost $4. It's $4 per pound. Okay. So let's first write an inequality stating the number of pounds that you're going to be purchasing, consisting of blueberries and strawberries. If I buy a certain number of pounds of blueberries and combine it with a purchase of a certain number of pounds of strawberries, I will be getting 3 total pounds, but not so fast. It's not an equal sign. We need at least 3 pounds of fruit. So can we have 3 pounds of fruit? If we need at least 3 pounds, can we have 3 pounds of fruit? That answer is yes. So equal to is a part of the set. However, should it be less than or equal to 3 or greater than or equal to 3? Remember, 3 is the barrier. It's that threshold. It's the boundary. And we state, do we go on one side or the other? Let's find out. At least 3 pounds. That means 3 or more. Our purchases, need to exceed 3 or be equal to, greater than or equal to right there. Now I'm going to graph these. Let's go ahead and graph these on the fly here because I just wrote this one here and they do say graph on the same plane here. So I'm going to go ahead and let's actually color code this thing. Let's do green for this guy here. So my green one is going to look like, in standard form, I can graph this out of standard form here. Pretend like it did say equals. X equals 3 is your x-intercept, and y equals 3 is the y-intercept. I'm playing my hide and divide. If you want to, you can put it in slope-intercept form like this. I'm just saying that you can do either or. Trust me, I'll be doing both, but with my teachings, I am assuming you have seen some of my older videos for this, or you have some way of going about graphing. Because for me, it's not about teaching you how to graph right here. It's about teaching you how to set up the word problems and interpret what your solutions mean. So if you do have other questions on how I go about graphing some of these, I do recommend, I do recommend that you check out some of my previous videos on the subject matter. Just the last couple videos will do. Okay, greater than or equal to means a solid boundary line here, and I will go ahead and shade above this guy. Because what you're doing is you're testing, I test 0 and 0 on x and y. I test the origin, and 0 is not greater than or equal to 3, so I will not shade on the side where I test 0, 0. So I'm going to be shading above right here. Okay. So all of these right here, to make sense of our problem and what we're looking at, all of these right here, the shaded points, if you assume they're integers, and let's pretend like together that what we're talking about when we're purchasing pounds of blueberries and strawberries, that you can only buy them in integer amounts. Meaning, I can buy a pound, like they're out of a bag. I can't buy half a pound. They come in pounds. So, all of these state the amount of pounds that we can purchase. Like I can purchase 3 pounds of blueberries and 5 pounds of strawberries because that is greater than or equal to 3 pounds. Now we'll talk about more of that stuff down the road. All right, let's do the next graph here. You can spend at most $21 on fruit if blueberries cost $4 per pound, strawberries cost $3 per pound. All right, I'm not going to get too deep into the idea of writing these ones out. Again, we've done this kind of stuff before. If you take $4 per pound of blueberries times the number of blueberries, that's how much all your blueberries will cost. And if you take $3 per pound of strawberries times the number of strawberries, that's going to be that guy right here. Now, our total amount spent cannot exceed $21. We can spend at most $21 on here. So we can be equal to, most of these I think will be equal to as well as the greater or less than. I can't actually think of one that's not in these 4 problems. Less than or equal to $21. This is amount of money spent. All right, so if I were to graph this one right here, I do want to get this one in slope-intercept form because I do not want to divide 21 by 4. So I'm going to subtract 4x from both sides, and then I'm going to divide everything by 3, and I get y is less than or equal to negative 4/3 x plus 7. Again, I divided everything by 3 here. This is rewriting that guy right there. This one makes sense in context. This one is a little trickier to actually talk about, so I'm not going to, but it's easier to graph. So the y-intercept of 7, and let's go down 4 and right 3, and down 4 and right 3, and then let's go ahead and pick purple. Which purple? I think it's this one. Pick purple and connect the dots right here. Okay, so here's the other guy. Now I do have to shade as well. And in shading here, if you test a point like 0, 0, remember that's my infamous testing point right here. Let's do it with the original. 0 plus 0 is less than or equal to 21. That's true. So I'm going to shade on the side that includes 0, 0. That means shading underneath the line here. So in shading underneath this line, it's going to be looking a little bit like this right here. And then you're seeing this intersecting region. Okay. Now I'm going to mention a little bit more here. I only created two inequalities right now. I'm actually going to create 2 more. You don't have to write them, but you're going to make sense of what I'm talking about here. There are, in most word problems, an implied inequality set. And you'll see what I mean right now. I'm going to be making these 2. X is greater than or equal to 0, and y is greater than or equal to 0. These implied qualities tell us this. We can't buy negative amounts of blueberries and strawberries. We just can't. And we can buy 0, meaning we can buy maybe all strawberries and we might be able to still exceed 3 pounds and still spend under $21 and things like that with buying 0 blueberries. We can do that, but we can't spend negative. And if you look at shaded region stuff that I talked about, where I said, like, remember how these are solutions to these? I can't buy -1 blueberries and 1 strawberries bag. I can't. So I should be restricting myself on all of these. Now, I'm not going to shade it in, but what I'm going to do is really bolden my X and Y axes, and I'm just going to erase the shaded region that is not involved with this stuff that we're doing right here. So I'm going to bolden these a lot more and say I got to be within the first quadrant here. Okay. So I'm just going to go ahead and erase anything that exists outside of the first quadrant. I don't know why that happens here. It looks kind of cool, though. It looks like flex. F-L-E-C-K-S. Interesting. Okay. So this solution set right here is what's going to reduce us with what we can and can't have. Okay. I don't know why that got kind of like that, but that's okay. Okay. So what we do get to talk about right now here, though, is the intersecting region. The intersecting region. And remember, the implied inequalities keep us within the first quadrant right here. The intersecting region is this area right here. I'm going to highlight it more in red. I'm not going to shade it again, but it's this area right here. This is the area where we are satisfying both inequalities, where we look at buying at least 3 pounds of fruit and spending at most $21. Now, I said before, let's assume you can only buy integer amounts of poundage. I can buy 1 pound, 2 pounds, 3 pounds. Can't buy half a pound. I'm going to show you how many different points of intersection, how many different integer solutions there are within the shaded region. And remember, on the solid lines, count here. So all of these count. This doesn't count because this is not hitting an integer on y, even though it is on x. So far I've plotted 9. That's 9 of them. 10, 11, 12, 13, that's inside of it. This is right on line. 14, 15, 16, 17, 18, 19, and 20. It just fits with inside. There are 20 different possible solutions that I can do. And there's a finite number. It's not infinite, but there are 20 possible solutions that I can have here where I can buy a certain number of pounds of strawberries and blueberries and keep it over 3 pounds, at least 3 pounds, and at most $21 spent. And that's what's cool about this. The shaded region tells us what we can be within. Okay? All of these are solutions. Now they say identify and interpret a solution to the system. Okay, so I'm going to take, now you didn't have to plot all these. This is just showing you that this is the number of, and this is what all these tell you. So I'm going to go ahead and pick this one right here. Let's see. Just make it kind of a green. That one right there, let's do blue, is the one that we're talking about. And in this one, I'm going to state that that's 2 for X, 3 for Y. That's 2 pounds of blueberries and 3 pounds of strawberries. So identify and interpret a solution. Here's a solution. Let's interpret it. You can purchase 2 pounds of blueberries and 3 pounds of strawberries. Now, I'm also implying within this that I'm talking about you can buy these things and you will at least have 3 pounds and you will not spend, $21, more than $21. How much money would you spend, by the way? And how many pounds is that? 2 plus 3 is 5 pounds, obviously more than 3. $4 per pound times 2 pounds is $8. $3 per pound times 3 pounds is $9. 8 plus 9 is 17, which is less than $21. So that does work. Okay, last one. Use your graph to determine whether you can buy 4 pounds of blueberries and 1 pound of strawberries. 4 pounds of blueberries and 1 pound of strawberries. Yeah, that's one of our solution bits there. I'm just going to go ahead and say yes. You can double check it in the inequality things as well. All right, so that's it for that problem, and I will go faster on the other ones because I kind of explained all the stuff to begin with, and I know we've kind of went about 15 minutes into this one problem, but if you understand this problem, you can go into the other ones a little bit better. There will be a little more complexity involved with some of them. You'll kind of see why, but hopefully you followed along with this one as I start talking about the next ones. Okay, let's go ahead and move on. Number 2. You need to earn at least $120 per week working as both a manager at a grocery store. Grocery store. Sorry about that. That's my typo. And teaching music lessons. You earn $10 per hour at the store and $15 per hour teaching music. You are required to work at the grocery store at least 8 hours a week, but do not want to work more than 20 hours total. Okay. A lot of things that they say there. What don't we know? We don't know how many hours we can work at either job. All right, we don't know the number of hours worked. Okay, so let X equal, and let's do the first one. What do we do first? Grocery store. I'll just say number of manager hours. Number of manager hours. All right, and let's let Y equal number of music teaching hours. Let's just say music hours. There we go. Because we know how much you'll make doing those ones. And what we have to do is we have to go ahead and write out a system. Let's find the first one about the amount of hours total, because these are in hours, and I think it's the easiest one to kind of come up with that. So let's start with the idea of adding the amount of hours within a week, X and Y hours. We do not want to work more than 20 hours total. Okay, fair enough. So the amount of hours I work managing and teaching music cannot exceed 20. No more than, do not want to work more than, that's less than or equal to. Do not want more than, the opposite of more than, is less than or equal to. I can work 20 hours. 21? No. 10? Maybe. Depends on if we make the money here. But we don't consider that in this inequality. We write another one for it. You need to earn at least $120 per week. So greater than or equal to 120. So I'm going to do something here now. It's going to be greater than or equal to 120. And what we have to do is combine the amount of money made in the manager hours and the music hours. So we make $10 per hour at the store managing. $10 per hour times the number of hours gives us money made managing. And then plus $15 per hour teaching music times the number of hours there gives us how much money we make teaching music. It's greater than or equal to 120. All right, I talked about implied sets before, like the X is greater than or equal to 0, Y is greater than or equal to 0, and those apply here. They do. However, what I also want to talk about is the fact, because, you can't be having negative hours worked, and maybe you can work 0 hours at one or the other, but you can't for the grocery store. There is one little caveat here that says you are required to work at the grocery store at least 8 hours a week. Now here, we don't actually have an inequality for this yet. And maybe I can take one of these implied inequalities and use that. If X is the number of manager hours, can X possibly equal 2? Well, no, because we got to work at least 8. X has to be 8 or larger. So what I'm going to do is cross out this implied inequality right here, and instead within my system, it's not implied, it's very, very specific. I got to make sure I have it. X is greater than or equal to 8. We have to make sure that we exceed that amount. Well, we can meet that amount, but we have to make sure that we don't get under 8 hours worked as manager. It's something your boss is just telling you, or well, you're the manager, but something you just gotta match. This one's still implied. In other words, I'm still looking within the first quadrant only. However, we got to do this one here. And let's just talk about graphing that one first. X is greater than or equal to 8. And I'm going to go ahead and this is a different looking graph. It's going to be a vertical line. Now, remember, x equals 8 is a vertical line right here, but now we have to do greater than or equal to. I've not talked about greater than or equal to when comparing x, but I have with y. And with y, when we talked about greater than or equal to, we always mentioned that you shade above if y is greater than, you shade below if y is less than. This is a vertical line. I can't shade above or below it. I can only shade to the left and right. And that's what we're supposed to do. We're now comparing x to a value. And if x is greater than, then we either shade above or below. So I'm going to go ahead and I'm going to shade, excuse me, not above or below, right or left. Greater than means to the right. Right? Greater than means to the right. So I'm going to go ahead and shade to the right of this guy right here. By the way, as I slowly shade, and as you possibly slowly shade as well, recall that, well, I don't have to shade that low, but that's okay. I'll erase that part. Let's just do that again. Recall that we have to shade above the y-axis here because the implied probability. Okay. Now, people have asked me before in the past, and you might be willing to ask me here as well, Mr. Robinson, does that then mean that we can only work as many as 12 hours teaching music? Because if you work 8 hours if you're required to work 8 hours as a manager and you can't exceed 20 hours, well, 20 minus 8 is 12. So it seems like the most you could do teaching music, if the least you could do is 8 for manager, is 12 by teaching music. And you would be right. However, do we have to write that as an inequality? And sorry about this little thing here. Do we have to write that as an inequality? Y is less than or equal to 12. I'm going to tell you no. You don't. What's going to happen is in our graph, it'll restrict that for you. It's kind of cool. It'll restrict it for you. You don't actually have to do that. Once you've set these up, that will do it for you. Okay. All right. Let's do that. X plus y is less than or equal to 20. Hide and divide. X equals 20. Y equals 20. Those are our intercepts. 2 points make a line. I'm going to go ahead and graph that line in between. Where's my sky blue? I think it's this one. Not quite. That's a little too different of a blue. I don't know where my sky blue is I've been using here. I'm just going to go ahead and use normal blue. All right. So do I shade above or below? 0, 0. 0 plus 0 less than or equal to 20. That's true. We should shade below. We should shade below. By the way, I think most of these, when it does say less than or greater than, I think will normally be above or below, depending on what you're kind of, using there, because the y value is positive, and it does have to do with y being positive that kind of makes that matter. So if, in case you're curious, all the less thans here will mostly just be shading under, the greater thans will be shading above. Now I am shading within the first quadrant. Even within the first quadrant of x, even though I can't exceed, or even though I should be exceeding the x equals 8 all the time, I just want to shade within this region and talk about this is blue in a realistic sense, meaning I'm not shading negative. That implied is still involved, if you know what I mean. Okay, and the last one, the purple in the middle, if I play hide and divide this time, let's go ahead and hide the y. 10x equals 120, divide by 10, x equals 12. So that's going to go ahead and put x equals 12 as an x-intercept. And then 15y is greater than or is equal to 120. Divide by 15, y equals, I think, 8. Y equals 8. So I'm going to go ahead and plot that guy right there. 2 points make a line. Let's go ahead and connect those dots. And then I'm going to be shading, I assume above here. It does say greater than or equal to. 0 is not greater than or equal to 120. So I'm going to shade above this guy right here. My XFL game is ending right now. There's another one that I'm interested in watching that I'm going to set up and play. So after I shade this thing, I'm going to go ahead and pause the video for a quick sec, queue up the next game that I wanted to watch, strange as that sounds, and then I'll just resume. So shading above right here. Shading takes the most time, and I like to use this dead air to talk about something, so I don't really know what just yet. besides the fact that the intersecting region of all three is this bit that I'm going to place in green right here. This is the intersection of all three of them, and that's that shaded region of all three. So I'm just going to pause the video for one very quick second. I'm going to queue up another game, and then I'll be right back right now. Okay, and we are back. You didn't miss me, but I missed you. All right. So identify and interpret a solution of the system. Now remember, we are within the set right here. This is our shaded region of all three guys. Let's go ahead and do a different color then. So within here, within the green, is all three of them combined. You can erase everything outside of it if you truly want to. Maybe that helps. I'll do that for this one just to kind of be different from the last problem. I don't know why it kind of does that thing. It's kind of neat. But anyway, identify the solution set right here. We are looking at, and I'm not going to plot them all, but let's pretend you work on the end of an hour each time, you know, to kind of make it a little more fanciful and say, oh, it's 4 to 5 o'clock. That's as much as I'm going to be teaching. Not to a half hour or anything like that. Let's do on the integers. So I'm going to go ahead and, it's kind of ugly. Where's it yellow? This is kind of yellowish. I'm going to go ahead and choose the point. How about 12, comma, I think that's 6. Because it's going by 2's right here. So 12, comma 6. So what that's telling me is that in satisfying everything involved, and I'll mention what they are in a second, satisfying everything involved where X is the number of manager hours, I'm saying you can work 12 managerial hours and teach, what is it, 6 hours of music in a given week. Okay. What does this mean? Let's see. It means 3 things. Number 1, I've worked less than 20 hours. You can work 20, but I've worked 18 hours here. That's less than 20. Number 2, I worked at least 8 hours as a manager. Okay, I worked at least 8 hours as a manager because I worked 12. Number 3, let's see if I made at least $120. Well, 10 times 12 is already 120. So that works just for my manager hours. But then I also taught an extra 6 hours of music where I made 15 times 6, that's 90. So I made $210 doing both of those. So I made my 120 per week. I did at least 8 managerial hours, and I did not exceed 20 hours there. All of these solution points do that are within here. And if you go right on the integer ones only, I think that kind of brings it up best. So again, it's kind of cool that this thing tells us all the things that we need to know about that set. This is not involved right there. Okay, so that's the second part. And the third part here is use your graph to determine whether you can work 8 hours at the grocery store and teach 1 hour of music. 8 hours at the grocery store and teach 1 hour. Oh, that's not here. This is 2 hours right there. 1 hour would be this guy right in between there. Not in the shaded region of all three. That answer is no. You cannot. You're not, even though you worked at least 8 hours as a manager, and even though you worked less than, ooh, he's breaking away. Even though you worked less than 20 hours in the week, you did not make your $120 doing this. 8 times, what was it? 8 hours? 8 times 10 is $80, and then 1 hour of music is an extra 15. That's $95. You're not meeting your $120 quota. So again, it needs to satisfy all 3 of that one. And by the way, we're staying above 0 for hours. Okay, that's number 2. All right, number 3, you are fishing for surf perch and rockfish. Gaming laws, like fishing game, allow you to catch no more than 15 surf perch per day, no more than 10 rockfish per day, and no more than 20 total fish per day. And those are kind of real kinds of things. I don't know if those are the real numbers, but they limit you at times when they are able to. Man, that guy can run. Touchdown. All right. So, this is all about number of rockfish. We don't know how many rockfish and surf perch. We don't know how many, but it's not about cost. It's not about weight. It's just all about number of. Every bit of this inequality set is going to be about number of. So let's let X equal number of surf perch caught. I'm just going to write number of. Hopefully that's okay. And let Y equal number of rockfish. Okay. Okay. This one right here, ooh, there we go. This one right here, let's set this bad boy up. We cannot catch more than 20 total fish per day. So when you add these, I'm sorry, my eye's itching. When you add these all three together, or these two together, we cannot have more than 20. We can make 20, but less than or equal to. Okay. No more than 10 rockfish, no more than 15 surf perch. So surf perch is X, no more than 15, and then rockfish, no more than 10. And that's what those things are telling us there. Now implied, and I'm going to put it kind of in black right here, implied we are still greater than or equal to 0. Can't catch a negative amount of fish. You can catch 0. You might not catch a bite out there, but we have to stay between 0 and 15 on X and between 0 and 10 on Y. And again, those two are implied. All I mean by implied is that we're going to say no duh. We are going to be in the first quadrant only. So let me just restrict the first quadrant bits right here and just make sure I stay within that shaded region. The bigger, the bolder, the easier for me to know. All right, let's do the green and purple ones first. Let's start with the green. X is less than or equal to 15. X equals 15 is this. Let's see, 13, 14, 15. It's going to be between 14 and 16 here, and it's this vertical line for X equals 15. And remember, I am making it solid. And less than or equal to, I'm going to be shading to the left. Okay, I'm going to be shading to the left here. Now remember, I am going to be keeping within the first quadrant though when I shade. So it's going to be this guy here all the way down. And, shading's the part that takes the most time. But again, these three will kind of keep within the barrier of what it is we can and can't do. Da 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 da. I really have to change the tip of my pen now because when I do this, it's really wearing this thing down. This thing at the tip right here. Probably have to change it out after the end of this video. All right, Y is less than or equal to 10, but also above 0, of course, as we talked about. Let's go ahead and do that one. 10 is, there's 8, there's 12, so here's 10 right there. We got to stay underneath that. Purple. So I'm going to be in the first quadrant underneath that. Remember, I'm not just shading the selected region. And I think for the last problem, maybe I just will. Maybe I'll only shade where it only intersects. But I'm showing you right now what Y could be if we weren't restricting anything else. If we weren't restricting X and if we weren't restricting our total number per day there. But that's the shaded, the intersection shaded region, region of both. But could I catch, say, 14 rockfish, surf perch, and 8 rockfish? Well, we'll see if that really exceeds within here. So let's draw this last one and make sure that we're within that last guy. So the last one in blue is going to be X equals 20, Y equals 20 as both of the intercepts. And let's connect those two dots right there. I really should be putting arrows on these, but because I'm within the first quadrant, it's like, I don't really have to. So less than or equal to in this case, because 0, 0 is satisfied within here, we're going to be shading underneath. And it, of course, again, like I said, in shading underneath, I am staying within the first quadrant. So here's the last set here. As I begin the shading and finish it off. All right. So the final shaded region is going to be this shape that is right here. I'm just going to make it nice, big, and bold. That guy right here. And that includes anything that's on those boundary lines. I think that was a little boisterous. Let's go ahead and shrink those guys a little bit. There you go. And that shaded region right there. Now, the question that comes up after this is, sorry, I'm trying to move these little lines here. I'm a little picky about it. There we go. Okay, use your graph to determine whether you can catch 11 surf perch and 9 rockfish. And remember, and do you have to use the graph? No. Generally, it's better to use the graph because you're just looking at a shaded region. The only problem with the graph is the scaling. These go up by 2s. So 9 is right here. Oh, 11 for surf perch is right here. And 9 for rockfish. Ooh, that's right on here. So there are two problems with the graph right here. Number one, we're we're in between our little integer, our scaling increments right here. So are we right on the line or is it actually above? And number two, the inequalities right here actually might be easier to do because the math is very simple this time. We're doing 11 plus 9, that is 20, and that's okay. 11 is less than 15 and 9 is less than 10. So it does actually check out and it is right on the boundary line. So that is okay. This is a yes to this guy right here. That one was allowed, as well as anything else in between. Oh, I did this graph thing wrong. I'm sorry. Right here. Hopefully you guys were calling that out as I did that. That was by no intent. By no intent was I doing that on purpose. There we go. That's the region. I was wondering why. I'm like, are we just taking out that one triangle? No, we're taking out that one as well. I'm sorry about that. When I actually even saw this to begin with, I knew it was going to be that. But so yeah, this is not okay. This is not okay right here. Just within the red border. It is allowed. Sorry about that. All right, that's it for that problem. And again, anything within here is fine. It's nothing about cost or anything like that. It's just within this region. That means 0, 0 does work. You can choose not to fish and you won't get in trouble. All right, let's go ahead. Last problem. Number 4, on a road trip with a friend, you drive 70 miles per hour and your friend drives 60 miles per hour. The two of you want to drive less than 15 hours and at least 600 miles per day. Your friend will drive more than you. These aren't unrealistic kinds of things that you can talk about, all right? Maybe it's something like it's your friend's car, so he's the one who wants to, drive more than it. I would say that for my car as well. I'm like, okay, I'll let you drive a little bit, but guy, don't drive more than me, man. It's my car. I don't want to mess something up, anything like that. I'll catch a little sleep. And your friend's just a conservative driver. You're a little more aggressive, whatever it is. Maybe the speed limit's 65, and he doesn't live on the edge. You do. Drive less than 15 hours. That makes sense. You don't want to be in a car forever, but you want to cover some distance. Okay, so all of these, again, it's within realistic realms to talk about this kind of problem for a certain reason. This does apply in the real world. When people say, when are you going to use this in real life? You could actually use these things to map something out and say, what does my solution set tell me? Okay, so let's go ahead and write and graph that system. Now, what don't we know? We don't know how many hours each of us are going to drive. Okay? We also don't know how much distance we're going to cover, but that's based on the miles per hour. When we multiply that by number of hours, then that kind of gives in. Okay, so that's the other thing we don't know. Let's see, how do I want to say this best? 2, you want to drive around 15 hours, at least. Okay, so let's do this. Let's let x equal number of hours driven by you. Okay, and then let's let y equal number of hours driven by friend. Okay, and then what we're going to get from that is mileage when we need it. By friend. There we go. Okay, so let's go ahead and use the definitions and create some inequalities. You drive 70 miles per hour, your friend drives 60. Is there some sort of x is greater than 70 or anything like this? No, this is information we're going to use later when we talk about number of miles total. Here's the information we need. 2 of you want to drive less than 15 hours. The 2 of you total, you do not want to exceed more than 15 hours. So, no, it just says less than. It doesn't say less than or equal to. Oh, this one just says less than. You want to drive less than 15 hours. 15 hours isn't okay. 14 hours, 59 minutes apparently is. Whatever, that's what it says. And at least 600 miles per day. So the next one is where we apply this stuff. If I multiply 70 miles per hour by the number of hours that I drive, that will give me how many miles I've traveled. For example, 70 miles per hour times 10 hours is 700 miles. That's for me. For you. For friend, it's 60 miles per hour times the number of hours driven right there. You want to drive at least 600 miles per day. So this needs to be greater than or equal to 600. And of course, the implied ones, once again, x and y are greater than or equal to 0. I'm not going to write them this time. They are implied. Better left unwritten. I'm going to go ahead and bolden that, though, and make sure that we stay within that boundary. We're not going to drive negative hours. Is there even a chance? Oh, hang on. There's one more. Hang on. I'm missing one. Your friend will drive more than you. Your friend is y, number of hours. Your friend will drive more than you. Now, does that mean hours or miles? That's a good question. I'm going to go ahead and possibly falsely, I'm going to go ahead and assume this means hours. Okay? Your friend will drive more hours than you, not more distance. Because if your friend's driving more distance than you, and he's driving more slowly, then that's going to mean, because it's going to take longer for him to get there. Sorry, not greater than or equal to, just greater than. Your friend will drive more than you. There we go. I'm sorry about that. That's the last one. Y is greater than X. Okay, so let's go ahead. And again, what I said before was greater than or equal to 0, things like that. Is it possible that you can drive all the hours or your friend can drive all the hours? Obviously, it's not possible that you can drive all the hours. Let's start with that one first. Y is greater than or equal to X. How do you graph Y equals X? Well, that's Y equals 1X plus 0. That's a 1 for slope and 0 for y-intercept. So we are going to actually be just rising 1, running 1 from the origin. We're just making a diagonal line going across this way. Now I'm going to make it dotted because it is only greater than. It's not greater than or equal to. Keep that in mind. So it's going to be looking like this guy right here. Whatever y is, or whatever x is, y is going to be the same as far as the line. But now as far as actually shading it, y is greater than x, we shade above. So shading above here looks like this guy. So it's going to be impossible for your friend to drive 0 hours and cover any of the scenario stuff because your friend has to drive more than you. And if you're not driving any hours, then then your friend's not driving any, and then that means you're not covering any distance. Excuse me, if your friend's not driving any, that means you're not driving. I didn't know what that was. I think it was some weird motorcycle. All right, so that's shading above. I don't know if the mic caught that sound outside. I thought it was a lawnmower, but then a lawnmower zoomed across my road. Okay, it's not a private road, but it's a resident road. It's like a dead end. It's a you don't pass through my road to get to a main street, basically. All right, blue, x plus y is less than 15. Again, 15's not right there. But hide and divide, I get y equals 15, x equals 15 as these two guys right here. And I'm going to connect those two dots. And, I want to finish this video. I didn't know it was going to take as long as it was going to. Oh, less than. I need to make it a dotted line. I can't make it solid here, so I can change that. You can always go to the eraser. And less than, 0 plus 0 is less than 15, so we shade on the side with 0, of course, as I said last time. And we are going to be shading this way. So you're starting to see the set for which this can work. It's really limited so far. By the way, we're going to limit ourselves even more with our last set, I assume. Otherwise, it probably wouldn't have been talked about. So let's see the last one. 70x plus 60y is greater than or equal to 600. I really want to change this one into slope-intercept form. Subtract 70x and divide everything by 60. So y is greater than or equal to, I'm going to reduce the fraction. Negative 70 over 60 is negative 7 over 6. Negative 76x plus 10. That's a 10 right there. 600 divided by 60. So y-intercept of 10. Let's go down 7. Remember, going down 7, remember, this is 10. So going down 7, we're going to get to 3. Okay, and over 6 is right there. That just helps me find one of my sets of points. I'm just going to go ahead and connect those two because beyond that, I don't really have information. What are they doing? What's this guy doing? I don't really have information that I can use to kind of get another point because I ran out of grid line marks here. But I'm going to run through this point. It is a solid line. Good God, guy. It is a solid line. And I'm going to be shading above that one as the greater than or equal to. We've kind of talked about that. Oh, actually, this is greater than or equal to. Yes, it will be shading above. Now, I've mentioned in other videos, in standard form, greater than or equal to doesn't always mean shade above. It does have to do with y's sign, though. If y is indeed, oh, not just that, also this as well. If y is indeed a positive number and it says greater than or equal to, and you get y by itself, all that, it will be shading above. However, if y is negative, the inequality does flip because you end up dividing by a negative. But it's easier for me to say test a point or put it in slope-intercept form yourself, so you're not memorizing that bit and you don't confuse yourself with what you're talking about. God, I really got to change this thing out. All right, I'm going to erase all the other stuff that I drew here, and I'm just going to show what remains here. It's the intersected region that's going to get very splotchy. I guess what happens when I erase this is it starts to, I don't know what it's doing. I guess it takes the amount that I shaded with the lowered opacity and it clumps it into that last opacity set. So it makes it look like this weird. Isn't that weird? And look, oh, it just got less weird. That's weird. All right, this is the combination of all three. This boundary, what the? Oh, never mind. It got more weird again. I could not explain to you what the programming is that went behind what makes this happen. Because, you know, things like this don't just happen automatically. This was somehow programmed to happen. All right, within this shaded region right here, and within these, now I'm going to purposefully dot these bits. Within this bit right here is what we can do. Okay. How many hours can you and your friend drive per day? So, you know, there's more than one answer. And obviously, when it comes to time, you could drive half an hour. You know, you could drive half an hour. But for the sake of it, let's talk about the amount of hours we could drive. Say we just chose to do hours. We say, okay, we're just going to do on hour marks, all right? You could, theoretically, based on this, you could drive 0 hours, and your friend could drive 10 hours, 11 hours, 12 hours right there, 13 hours, 14 hours. I guess not 15. Because, look, you don't want to exceed 15 hours driven a day. So, you know, you could drive 0 hours. Your friend could drive all of them. That actually does work. I'm just going to pick a single one. Let's pick, like, this one right here. And let's talk about what that one says. Because I want to wrap up this video. This went a lot longer than I did anticipate. However, hopefully you're learning something along the way. All right. How many hours can you and your friend drive per day? This is, for example, you can drive 4 hours. And your friend can drive 10 hours. And that does a lot there. You know what? And by the way, this isn't something that I've kind of brought up just yet, and I'm not going to be talking about it in this video. This is not the extent to which we can do these kinds of word problems here. The really, really cool thing we can do with these word problems is talk about what's called optimization, where you're either maximizing or minimizing something. For example, I might want to, and I'm not going to talk about it here, but for example, I might want to maximize the amount of distance traveled, but minimize the number of miles driven. Excuse me, the number of hours driven. Maximize the amount of distance traveled, but minimize the amount of time driven. Right? Why would we spend all 15 hours, about 15 hours of my friend driving, if I drive faster? Okay. Now, that's not to say that I can drive more than him. Remember, that's one of the restrictions. I can't drive more than him. But why wouldn't we make the 15 hours something a little more shifted so that I'm driving more of them because I drive faster, we'll cover more. You know, something like that. Or in previous problems, we talk about something involving costs and stuff. Maybe I want to minimize the number of hours worked, but maximize the amount of profit. And it's possible in this shaded region stuff to do that. I'm not going to talk about it, but there is a way to go about doing that kind of stuff. Same thing here. Maximize the amount of pounds of fruit purchased, but minimize the amount of spending. It is a possible thing to do. I think it's called linear programming. It's nothing I'm going to be covering here. It's something I could cover, but it's nothing for my particular math classes, so I will not. But it is a cool item to talk about. And hang on, iTunes popped up. It is a cool item to talk about, and it's something that is worth discussing some point in the future. All right, but that ought to do it for me right here. That is all that I'm going to talk about with this stuff. The next video that I'm going to do covers, why isn't football on? What's happening? This was a streamed thing, so it looks like this guy is going through VPNs or something to make sure he gets some football. And there it is. All right, but that ought to do it for me here. The next video I'm going to do is going to be an overall cumulative sum of setting up systems of equations from word problems, graphing systems of inequalities, and then setting up and solving systems of inequalities from word problems as well. Also solving systems of equations. But that's all it. Hopefully you enjoy this one and the next one that comes up. Take care, guys. Bye.